Good afternoon, everyone. Welcome to our next event, part of the Enrichment Week for MSc Big Data Analytics students and also for mathematics students at the University of Derby. Our next speaker is Lucia Cavallaro, PhD student at the Data Science Research Center of the University of Derby, who will present us her PhD topic, which is related to graph and the network theory for the analysis of criminal networks. Lucia will give us more details of the technical part, but what is very interesting is that as part of her project, she was able to construct networks, so networks based on real data, and then designed algorithms to understand the structure of criminal networks, and then also to understand how could this be disrupted. In terms of bio, I can tell you about Lucia that she achieved MSc cum laude in engineering and computer science. So this was from the University of Messina. And then also she has like a BSc, of course, in computer science. And her PhD research involves network science, deep learning, data analysis, and also, she published a paper in PLOS ONE related to this work, which was accessed more than 3,000 times in just the first 3 months, and also it caught the attention of the press across multiple continents. We look forward to listening your presentation, Lucia. Thank you very much.
Thank you, Ovidiu. And indeed, I would like to thank you for the opportunity to present this piece of my research today at this tutorial session. And I hope it also could be useful for students who will see the recording afterwards. As you said, I'm Lucia Cavallaro, a third-year PhD student in computer science here at the University of Derby. And today I'm here to show you the criminal network aspect of that work that me and my colleagues coming from several international universities have been conducted so far. But first of all, I would like to give you just some basic information about this topic. And indeed, the network science is a combination of several fields. Among them, there is the graph theory from mathematics that allows to study complex networks. For complex networks, we can consider several kinds of topologies, for example, telecommunication networks, or also transport networks, or also social networks such as Facebook, Twitter, TikTok, and so on. So to just sum up, the graph theory is the study of graphs that are mathematical structures used to model pairwise relations between objects, and graphs are composed by vertices that are connected by edges. This translates in network science, that is an academic field which studies complex networks, and it takes some concepts from graph theory. In network science, the networks are composed by nodes that are connected through links. And lastly, there is the social network analysis, that is the process that investigates social structures through the use of both networks and graph theory. Okay, but what happens when we are dealing with criminal networks? Because the problems are more, there are more problems in dealing with those kind of networks. First of all, there are problems in data availability and reliability, because those networks are also characterized by covert nature of the most influential people within the criminal organization. And then also the investigations are conducted by law enforcement agencies, then they are difficult to find available online and to analyze them. So there are quite a few data sets available on which we can work with. Next, since I'm dealing with mafia networks, that is a specific kind of criminal organization, it works also quite differently from other criminal organizations, for example, terroristical ones, because they are, first of all, more structured in terms of the connections between criminals are stronger, since they are, most of the cases, part of the same family. Next, they are organizations that last for several generations. And they are also characterized by the reaggregation of the clan even after reaching their goals, and they also diversificate their illegal activities. For all of those reasons, the state of art is plenty of qualitative studies, but there is a shortage of quantitative ones. Then on those kind of networks, several questions may arise. For example, who is the boss? How can be detected? How can we dismantle those kind of networks? For example, if we want to slow down the information spreading across the network by arresting the most influential individual within the clan. Or, for example, if we can define some kind of threshold of data inconsistencies from law enforcement agencies that are still tolerated in order to still being able to analyze properly the criminal network. All of those questions may be summarized by how may we investigate the behavior of those real criminal networks. And our questions are our answers has been through network features. In particular, we have used social network analysis in order to reduce the complexity of those kind of networks. Before to move on the details of the research, I would like to give you just some details in terms of theoretical concepts that have been followed so far. So let's start from the very beginning on what is a network, what is a graph. That is a picture representation that shows data organized in a certain manner. And networks are characterized by, as I said earlier, by nodes and links, where nodes are the terminal or intersection points of a graph. In a criminal network, the nodes may be represented, for example, as I've done in this picture, by the criminals, the suspects that interact among each other through a link. Indeed, the link represents the connections between the nodes. And in our case, the links may be used to represent phone calls or also face-by-face meetings among suspects or any other kind of relationships that those people may have among each other. Another important aspect to be considered is the weights of the links, because the networks can also be weighted. In this case, the links are represented having different sides to reflect the aspects of, for example, the interaction frequency or the cost. If we are talking, for example, on transportation networks for trains, the weight may be, for example, the distance between two cities, so in terms of kilometers, or also in terms of the cost to reach, for example, by plane, a certain city, for example. In this case, in criminal networks, the links may represent the interaction frequency. So, for example, the amount of phone calls incurred among two people. And in this case, if the graph is weighted, we can represent having larger links in case of a higher interaction frequency, and a thinner links could be used to represent a lower interaction frequency, for example. Another important aspect is the importance of a node. That, for example, in social network could be seen how can we find the influencer, so the ones having the higher number of followers, for example, within a social network, while in a criminal network could be how can we identify the boss or the network, or since it is quite difficult to be done for those kind of networks, it is more easily to detect the most the people that has a key role within the organization, for example, trusted people of the bosses to spread the messages, for example. And to represent these aspects in graph theory, we can use, for example, nodes having different kind of sizes. And to quantify, so how can we identify those nodes? As I said, the less influenced nodes within the network could have lower sizes. So, for example, in this case, at the periphery of the network. And to quantify their importance, we can use from social network analysis, for example, the centrality metrics. Among them, the easiest one to be computed, there is the degree centrality that takes into account only the number of links incident on the specific nodes to ranking the nodes according to their degree. In this case, for example, this node is more important respect with others because his degree is equals to 5, since it has 5 links incident on it, compared with, for example, these other nodes that has only a degree equals to 1. Another concept that has to be taken into account is the concept of a path. That is a sequence of links to connect a source node A to a destination nodes B, for example, with no links, no nodes repetitions, which means that, for example, a possible way to reach that node could be through these intermediate nodes and then reaching the final nodes. In this case, the path equals to 2, because we have done 2 steps to reach the final node. Of course, other possibilities are also possible, like for example, moving through these other nodes, but the work, so the moving from one node to another one, could have a cost that we also have to take into account the weights on the links if the network is weighted and so on. The last aspect that has to be specified here is the concept of connected component. It is a subgraph in which each pair of nodes is connected with each other through a path. In this case, the largest among the connected components is the graph itself, since there are no disconnected parts. But if we, for example, delete this link from the network, we can then obtain 2 connected components, and the size of the largest one is reduced from the whole graph to until a subset of it. To easily put all of those information within a visual strategy, I prepared this video that shows a comparison in using a proper centrality metric that efficiently ranking the nodes in order to disgregate efficiently the network, compared with an approach that is not efficient in this specific case. Here I'm showing you what happens when using the between centrality compared with the random removal of nodes. And as you can notice, the largest connected component size is fastly decreasing in the case on the left, while it's still quite high on the right, having into account the same number of nodes to be removed. So, for example, here you can notice that the largest connected component size is equal to 5, which means this small subgraph, let's say, while in this other case, with the random removal approach that wasn't efficient at all in this case, the largest connected component size is still quite high, so it is quite well connected, let's say. Talking about the approach I followed to conduct this piece of research, I've first of all we have obtained 2 graphs from juridical acts that are 2 weighted graphs, and with those 2 graphs we have then conducted some kind of social network analysis through shortest and average path length analysis, weight distribution, centrality metrics, and so on. In particular, the simulations that I'm showing you today relates to the network's disruption aspects. And in particular, we are pruning the network, simulating the event in which law enforcement agencies is arresting some suspects that are part of the criminal organization, and then we compute what is the damage in terms of network fragmentation after the removal of those aspects from the network. In order to do so, we have used several kinds of centrality metrics to use different strategies to ranking the nodes, to identify the best ones that can cause a higher damage of the network. And to evaluate the amount of damage, we have then used the average path length and the largest connected component size. The datasets that we have obtained and the 2 graphs that we have obtained from the datasets are herein shown, that are both the graphs are complementary to each other because they represent the same clan of an investigation that concluded in Messina and Sicily in 2007. And the investigations has been conducted by the special operation units of the Italian police. Here I'm showing you on the left the graph in which the links represents the phone calls that have been spotted between the suspects, while on the right there are the connections represents the face-by-face meeting that the people had within the network. The colors also represents the clans that interacted among each other, and the cycle nodes, for example, like this one or this one, represents the bosses of the clan, and all the white nodes that maybe I don't know if you can see them. The white nodes are all those suspects who are close to the family, but it wasn't possible to classify them in any of the previous categories. And the node size and the link width is also proportional to the interaction frequency. Here I'm showing you just a quick summary of the main statistics that relates the two graphs. And in particular, there are 47 nodes in common, which means that the same people have been spotted by law enforcement agencies to have both face-by-face meeting and phone calls among each other or with the other members of the clans. In terms of methodology followed, we have conducted a preliminary analysis to understand how the graphs are composed, how the networks are made. And then we have computed the shortest path length and the weights distribution in order to have more information about the network. Then, through the use of Centrality Metrics, we, as I said earlier, we have reduced the number of nodes of the network, and then we have evaluated the effect of the disruption process through the average path length that if the fragmentation level is quite significant, is supposed to be larger after the node removal process, while the largest connected component, as you have seen in the previous example, is supposed to be reduced after the fragmentation process. In terms of centrality metrics used, we have used the most famous one, the most popular one and well-known in network science, that are the degree, cuts, betweenness, and collective influence centralities. And in terms of strategies to simulate the fragmentation, we have removed nodes according to two different scenarios. From one side, the sequential one, it simulates the event in which the police is arresting people one by one, while the block approach simulates a raid, a police raid, then a group of people are arrested at once. From the analysis, here I'm showing you the shortest path length analysis first, while on the left there are the unweighted scenario in which we didn't take into account the weights of the link of the networks. Then the weights were all equals to 1, while on the right there is the weighted approach. The blue columns represents the phone calls dataset, the meeting datasets, while the orange one represents the phone calls dataset. From both the graph, you can notice that there is a higher interaction frequency with a balanced number of intermediates, for example, here. And a possible explanation could be that if people within the criminal organization have a lower number of intermediates to share a message, then the source node could be exposed and could have some risks to be spotted by law enforcement agencies, for example. And the same could happen in the other extreme scenario. So if everybody is used to share a message, then it's too risky to do that. Also because there is some kind of hierarchy within the Sicilian mafia clans, and then they tend to share the knowledge with and messages with trusted NK affiliates, not with everybody within the clan. Another aspect that in the unweighted approach is a bit hidden is that the phone calls has a lower frequency. And this is a possible explanation could be that to reduce the interception risks, they prefer face-to-face meeting because through phone calls, for example, they don't have the chance to understand if the phone is under surveillance, for example, or not. Then, from the weight distribution analysis that here I'm showing you on the left, the meeting datasets, while on the right, the phone calls one. Here we are plotting what is the probability to find links having a certain weight within the network. In this case, it means that the majority of the links within the network have a weight very, very low or equals to 1, which means like an unweighted network, let's say. And there are just a few nodes having higher weights in their links, in their incident links. This is could be explained as earlier with the tendency to condensate the interaction frequency in just some K affiliates, and they prefer to avoid connections if it's not needed, for example. In terms of disruption itself of the network here, I'm plotting the sequential approach only on the meeting dataset. And even in this case, there is the comparison between unweighted approach on the left and the weighted graphs on the right. And here we are computing the behavior, the variation in terms of largest connected component size after the nodes removal, after the removal of the nodes, accordingly with the centrality metrics that I've said earlier. As you can notice, there is an initial faster drop in the unweighted approach, but after a certain number of nodes, the trend is still quite the same in both the graphs. And this can be explained through the weight distribution that we have seen earlier, in which there are just a few nodes having higher weights. Then if you remove those links, then the network can be considered as unweighted. Next, you can also notice that the drop is faster with the blue curve that represents the betweenness centrality, and then this centrality maybe is the best one to fastly fragmentate this kind of networks. This is why we have then focused on this metric only, and we have computed the average path length and the number of connected components after the first iterations of nodes removed. So after the first 5 nodes removed from the network, and you can notice that as expected, the average path length is increasing as well as the number of connected components, while the largest connected component size is reduced, as you have seen from the previous slide. And just to conclude this talk, what you have found from this analysis was that from the preliminary analysis emerged that affiliates prefer to share their knowledge through K affiliates, and they also prefer face-to-face meeting, it seems, respect with having phone calls that can be more easily spotted by law enforcement agencies without that being known from the criminals' side. And also that the most effective ranking strategies in order to cause a higher fragmentation and quicker fragmentation of the network is the betweenness centrality. What we have improved in the state of the art was the use of new data sets. And then it was the main challenge of this approach, since it was a time-consuming process, and it has also been validated with the results, the graphs with the law enforcement experts. And these aspects also helped to improve the state of art in terms of having more quantitative studies respect than qualitative ones. Then in terms of challenges on this topic, the shortest path length analysis could help to have an insight on how those kind of networks work. Of course, working on those kind of networks, and more specifically speaking in mafia networks, it is still an open research field, but our datasets helped a bit in terms of having more datasets on which we can work on. Just a couple of slides on what else you can do with network science in dealing with criminal networks. You can, for example, use artificial network models, for example, the Erdős-Süreni and so on, to try to find an artificial model that best fit the behavior, the topology and the growing, the evolving network, let's say, in order to maybe in the future be able to understand how those kind of networks are made and how what can be the next connections of the suspects, for example. Another things that you can do is to investigate on the missing data. So to find a kind of threshold, that is what we have done in this paper, this other paper, a kind of threshold on the kind of data that law enforcement agencies may miss to recreate the criminal network. So like in terms of future works, we would like to use social network analysis, but combined with other metrics, maybe find more specific metrics that works better on criminal networks, for example, other centrality metrics, or define new centrality metrics, for example. Also, it could be interesting to dealing with temporal networks and conduct some kind of analysis if we have the chance to follow the investigations while they are going on. In this way, we can have different snapshots of the same organization and how things are evolving during that time. Another aspect that could also be taken into account is the human capital, combined it with the social capital, that is the classical approach. By human capital, we mean the specific skills of affiliates. For example, if there is a sniper, if there are some people that have pharmacological expertise and can produce drugs, for example, those are all aspects that at the moment are covered from those kind of networks, because we can only consider the links or the weight of the links. But if we can also include those aspects, the ranking could be different. For example, some nodes could emerge as relevant that at the moment are hidden. And lastly, we can try several kinds of configurations, or also replicate the same experiments, the same simulations on other datasets. So those are just the full references of the paper I've published so far related with this topic, in case some of you would like to have a more in-depth view on this kind of research. So that's it. Thank you for the attention, whoever is here online at the moment, and for everybody will join in afterwards watching the recording. And I hope you have found my research of your interest.
Thank you very much, Lucia, for a very interesting talk.